We were asked by Tom to avoid platitudes, but I just cannot refrain from expressing my feelings towards Richard, who had immense influence on me in many respects, which that's great. This talk is based on my joint work with a former student of Richard's, Pasha Kuyavsky, University of Minnesota, and is a result of the Russian-Ukrainian collaboration. The topic of the talk is linear incidence geometry. Linear incidence geometry studies things like this, what you see on the screen. So lots of lines in this case, some of them intersect in unusual ways. And there is a theorem behind this, as you can imagine. You require all of these miracles to happen except for one, and then the remaining miracle is forced to happen as well. Historically, the first theorem of this kind has been discovered, or at least attributed to Paphos of Alexandria. You take two arbitrary lines on the plane, you take 3 points on each of the lines, you connect them in the way shown here, you will find these 3 points of intersection, and magically they lie on this dashed line. So that's the first theorem of planar linear incidence geometry. The second theorem, historically second, is much more recent. 1639. It's a theorem of Desargues, which says that if you have two triangles in the plane, the red triangle and the blue triangle, and they have perspective from the same point. That is, when you look from that black point, the red vertices block the view of the blue vertices. Then when you look at the points of intersection of the corresponding sides of these triangles, these points of intersection will lie on the line. This is the theorem of Desargues. These are really the most fundamental results in dimension 2. In dimension 3, there is one such result which is plays a similar role. It is really quite recent, comparatively, almost 200 years old due to Möbius. It says the following: you have 6 points in 3 space. Let's think of them as being at vertices of an octahedron. Then there are some triples of these points, which naturally correspond to the faces of the octahedron. And 4 of these faces are painted pink here, and 4 of the faces are painted green. And Möbius' theorem says that if the 4 pink planes intersect at a point, which is a miracle, right? 3 planes always intersect at a point, but 4 requires a little miracle. So if the 4 pink planes intersect at a point, then the 4 green planes also intersect. Beautiful result. Of course, an actual question arises: where all these theorems are coming from? What is there some kind of general theory? Of course, there is a theory. I mean, books have been written about it over the centuries, but somehow it all looks like cottage industry, like some kind of ad hoc arguments. Each time you come up with something new, some kind of clever trick to prove the next theorem. And of course, it doesn't answer the key question of where the theorem came from to begin with. And the basic answer to this is that basically those people didn't think like combinatorialists. With the proper combinatorial insight, you can figure out what is actually happening. And that's the point of the talk. So again, back to history, following Möbius. 19th century was the golden age of projective geometry, people like Jean-Victor Poncelet, Michel Schall, Jakob Steiner, and Carl von Staudt essentially created the field. Here is the very first sentence from the famous Erlangen program by Felix Klein, which professes the development of projective geometry to be the most important advance in the last 50 years. Hilbert shared a similar view. Here is a quotation from his well-known book with Conforsen. Since the 19th century, projective geometry has occupied central position in geometric research. The theorems relating to incidence are by far the most important theorems of projective geometry. Of course, he meant more general results, not just linear projective geometry, conics, cubics, and so forth, and also tangency conditions, and so forth, and Schubert calculus more generally. But the most basic results, of course, are the ones that you have seen. But very soon, people changed their opinion. This is a quotation from Paul Dirac, the famous physicist, who was a big fan of projective geometry, who already in 1972 said that essentially all the low-hanging fruit has been collected. There isn't much to do, so this is not a fruitful research field anymore. Perhaps even more credible and impressive statement was made by Bob McPherson, who wrote in his paper with Mark McConnell, 1998. Notice the past tense, classical projective geometry was a beautiful field of mathematics. It died because, not because it ran out of theorems, but because it lacked organizing principles by which to select them, the ones that are important, and also was again isolated from the rest of mathematics. So this begs a few big questions. The first is, where are these theorems come from? I already asked that question. Which of these theorems are important and why? And what kind of other mathematics are they related to? So we attempt to answer these questions by suggesting what we think is the master theorem of linear incidence geometry, from which all other such theorems follow as special cases. As a result, we offer a uniform explanation for why these theorems hold. Of course, there are by now mechanical theorem provers. If you bring a theorem on a silver plate to somebody, there are already pieces of software that with minimal human input verify that the theorem is correct and even offer an irrefutable proof in the form of some kind of sequence of identities that check that certain polynomial belongs to some ideal. But it's still, we humans still want something better, at least at some point. Okay, so the construction involves tiled surfaces. So we are going to start with a surface of some genus, a closed surface, oriented surface, and we are going to tile it with quadrilaterals. Two examples. These are perhaps less exotic examples. So you start with a surface, you cut it up into quadrilateral, topological quadrilaterals. Everything is topological. There are no distances here, or curvatures or anything like that. Just you are thinking of each of these surfaces as a deformable thing. Okay. So each such tiling, we claim, gives rise to an incidence theorem. Let me explain how. So we start with the finite dimensional vector, projective space. And we take a tile whose vertices are labeled by points and hyperplanes in alternation. So A and B here are points, L and M are hyperplanes in the projective space. And we call such a tile coherent if the following incidence condition is satisfied. Well, first of all, I want to dispense with some special cases. I don't want any of these 2 points to lie on any of these 2 hyperplanes. And if A equals B or L equals M, then it is coherent. But generically, the condition really is that the line that passes through A and B pierces the quadimension 2 subspace at which L and M intersect. So generically, this is not going to happen because the sum of the dimensions is smaller than the dimension of the ambient space. But when it does happen, we say the tile is coherent. The simplest case is dimension 2. We have 2 points, A and B. We have 2 lines, L and M, and they form a coherent tile if the line that passes through A and B goes through the point of intersection of L and M. Okay, so that's the coherence condition. Now the master theorem. Suppose we have a tiling of an oriented surface by quadrilaterals. The vertices of the tiling are colored black and white so that we get a bipartite graph. This here is a torus, right? It's a hexagon, but you are expected to glue its opposite sides to each other in pairs. Then you get a torus. Okay. Now, we associate to every black vertex a point in our projective space. We associate to each white vertex a hyperplane in our projective space. And we require that none of these points lies on any of these hyperplanes, let's say. Then the claim is, that if all these tiles are coherent with the exception of one, then the remaining tile is also coherent. This is an incidence theorem manifested. Not only is it an incidence theorem, it's actually very easy to prove. Here is the sketch of a proof. We deprojectivize, each point becomes a vector, each hyperplane becomes a covector. Then there are pairings between vectors and covectors. Then for each, so these are some numbers that correspond to the edges of our tiling. Then for each tile, there is a mixed cross ratio, which is this thing divided by this thing, multiplied by this thing, divided by that thing. Okay, so the 4 pairings go into numerator and denominator in alternation. And 2 observations. The first observation is that the coherence condition precisely means that this cross ratio is equal to 1. And another observation is that the product of all these cross ratios is also equal to 1 because it's product telescopes. Every pairing appears in the numerator of the cross ratio on one side and in the denominator for the cross ratio on the other side. So we have a product of quantities which is equal to 1. If all of these quantities are equal to 1 with the exception of 1, then the remaining quantity is also equal. End of proof. So you are supposed to give at least one proof. At least one proof in a talk. Here is the proof of the main theorem. But so if it's so easy, why didn't people do this before?
That's the dilemma. COA is too much for something.
Okay. So the really surprising thing is that this is a master theorem in that all the theorems that you find in textbooks, including the ones that I mentioned and many others, experimentally, this is not a universality claim, but at least every theorem that has a name that we managed to find turns out to be a special case of the message. Now let me explain this in the cases of disargued couples. Which surface? So our paper has a quotation at the beginning, which is from Don Knuth, which said everything, science is everything that you can explain to a computer, art is everything else that we do. And so finding a surface is still an art. Okay? But what I'm presenting today is science, right? So once a surface has been identified, from that you get an incidence theorem in an algorithmic way. So don't ask me how, but I decided to look at this particular quadrangulation of the sphere, also known as Q. The black vertices correspond to points A, B, C, D. The white vertices correspond to lines P, Q, R, S. And these are the lines and the points that you see here in the picture. Okay? So P, Q, and R are the sides of the blue triangle, A, B, and C are the vertices of the red triangle. And then you check coherence. For example, the front face of the cube, AC and QS. Well, AC, this is the line. Where is the line? Oh, I ran out of battery. Terrible. Okay, I'll let this one. Okay. So AC goes this way, and F and Q intersect at this point, and that point surely lies on the line AC. Okay, that's the coherence condition. Let's take another one. This one, let's say CD, PQ. P and Q intersect here, here, and C and D are these 2 points, and the line CD passes through that point of intersection. See? So these 6 faces of the cube will correspond to certain 6 conditions here. If 5 of those conditions are satisfied, then the 6th one is, and you can easily convince yourself that that's exactly what this arc is. Now, oh. Well, it's no different. Can marvel at this in advance. All right, couples. So you would think, maybe you think, okay, now that I know the yoga, I should just identify some points and some lines in my configuration and come up somehow with some tiling and put those points and lines strategically into the tiling, and then it will fall. Unfortunately, it's not that easy, or maybe fortunately, because I believe that if that were the case, this would have been discovered a long time ago. So instead, you need to introduce 3 extra lines shown here in green. These are the lines that pass through these 2, these 3 points are not part of the story, but the lines of the triangle they form are, and these are the lines P, Q, and R, and you place them at 3 vertices of quadrangulation of the torus, and you place the remaining points here, and then you check everything works. So AD and intersection of PR, let's see, where is intersection of P and R? P and R, they intersect here, and A and D, well, that line sure passes through that point. Everything works, yes?
Is there an easy way to detect what the genus of the surface is going to be?
No. No. We don't know what the genus of the surface should be. It plays a role, but yeah, this is entirely an art. I have no idea how to algorithmically deconstruct the surface. But if you're teaching a class in linear projective geometry, you don't have to explain how you came up with it. You just show this picture, and this is the proof. So, like in old Indian manuscripts, right? A picture with a proof without any words. Once you know the yoga, that's the proof. Okay, so let's go on.
Sergey, a question. What about realization? So if you have a surface with the tiling,
Right.
does it always have non-trivial realizations? In other words, the theorem you will get, will it be always non-trivial or non-trivial?
Sometimes the theorem got trivial. We don't have examples where the modular space is empty. But thanks for asking, because this reminded me that each tiling doesn't give you just one theorem. It gives you a sequence of theorems in all dimensions. Because the master theorem holds true in any dimension. You can start with a tiling. And so we will see an example. Okay, yeah, maybe I should get distracted. Okay. So, this is the complete quadrangle theorem stated by Fomin. And you can sort of imagine what the theorem says. You take a red quadrangle and, 4 arbitrary points, draw 6 lines through them. They hit the black line at some 6 points, and you do the same downstairs with the blue stuff. And if 5 of these points coincide, then the 6th one should. And here's the proof. It's a certain tiling of the sphere. If you have time, and I gave you the slides, which you are welcome to get from me, and you could just sit down and check. The permutation theorem, another beautiful theorem. You can sort of imagine what it asserts, and here is the proof. It's a certain tiling of the torus. What does it mean? Okay, you find your favorite point where 3 of these lines intersect, and you say, you look here. And you say, let's not give that. That will be a corollary of all the other incidents. I'm not sure what to make of this, but yeah. All right. So now, can you get new theorems? Of course, because you can. Now we have a little shop where we can manufacture these theorems at will. Take any surface, and then take styling, and you will get a theorem. So this is we call it twin stars of David theorem. So there is a red Magen David here and a blue one, and they are kind of mutually inscribed. And again, you can drop one of the triple points and remove that condition, and it will follow from the rest. Yes, Alan.
So in your previous 2 examples, you didn't need to introduce new vertices edges.
I don't remember. Maybe we do, maybe we don't. Yeah. And this very simple tiling of the torus gives rise to that stars of David theorem. Okay, let's go to dimension 3. Nebu's theorem comes from this tiling of the torus. Again, you have to believe me. I mean, I don't have time to sit down and check all of these conditions, but sue me if that turns out to be correct. We checked it other people did. Here is a new theorem about 3 dimensions. So this we call it the 13 lines theorem. Take any 2 lines and 3 things. So this is only 3 things. Take any 2 lines, pick any 5 points on each of these lines, then draw these kind of vertical lines here, the 5. Then pick any point P1 on the middle red line, then draw the unique line through P1, which pierces M1 and M4. It will be this line, okay? The unique lines from a given point that pierces two given lines. And where it pierces will define point P2. And then in a similar way, we define P3, P4, P5, P6, P7, and P7 turns out to be equal to P5. Just imagine. This is what in the old German school was called Schließungssatz. So it's a closure theorem. You do something, do something, do something, and then at the end, you will return back. And this is the proof. The theorem comes from a genus 2 surface. So this is a certain. There are two hexagons here. You need to take a look.
You have to do it by hand, right? To go this diagram.
With the help of the computer, of course, yes. Using King's knee. Yeah, I mean, this was reverse engineering. You know, I started with this tiling.
So that's it, you start with it.
I mean, I told you, there is no false advertisement. I told you that this is a new theorem, SFTP. You see, these are my initials and questions. Okay. So we came up with this new theorem by taking this tiling and then seeing what it says. And that's what it said.
So you
So
can probably construct infinitely many types.
infinitely many. If I wanted to sell those theorems, you know, I would have hidden the master theorem from you and would just publish a paper every month. Okay, hold on. So let's take stock of what we have. The first problem is, which we don't know how to solve. Can we really obtain any theorem of weakness of geometry? We don't have a single concrete. Problem 2. Is there an efficient algorithm for constructing a tiling that delivers a proof, right? We already discussed this. There is strong evidence that such an algorithm doesn't exist, suggested by the obvious universality and settler phenomena. And problem 3, again, this issue has been brought up. What is the minimal genus of a tiling that proves a given theorem? In particular, can this genus be arbitrarily large? Does there exist a theorem that requires the surface of genus 100 in order to prove it? I have no idea. Probably, but yeah, since we don't know the relationship, we cannot go backwards, so we cannot really argue. All right, so let me now talk a little bit about, yes?
So do you have a theorem that has two different proofs of different genera?
Yes, and we have theorems that have different proofs with non-isomorphic tilings on the same surface also, and also different surfaces. Surfaces of different genera. Okay, so now let's talk a little bit about what some other mathematics that this is connected to. First of all, we notice that these quadrilateral tilings are dual to multi-curves, to nodal multi-curves on the surface, because we can just take each tile and connect the midpoint, so to speak, of the opposite sides of that quadrilateral to each other, and then keep connecting, continue these curves across neighboring tiles, and this will eventually close into a collection of curves. So Bizarre's theorem, for example, comes from the cube, and the cube corresponds to those three closed curves on the sphere, which we recognize as simply three great circles on the sphere, just intersections of the coordinate planes with the sphere. So that's what Bizarre's theorem corresponds to in this language, which is just cryptomorphic to the language of Thailand. And now you can see, for example, on the left, this is the multi-curve that corresponds to the Pappus theorem. Don't you recognize it? On the right is the permutation theorem. So instead of sort of looking for tilings, which may be a little hard to draw, you can just restate everything in the language of the model. Now, this is suggestive of something, namely, notice that a flip in a tiling corresponds to gluing in a cube. And that translates into a single application of Desargues' theorem, because as you know, Desargues corresponds to the cube. Let's translate this into the language of curves, right? And we recognize this transformation as the Reidemeister 3 move on the curves. And so theorems, which are equivalent modulo Desargues, correspond to multi-curves that can be obtained from each other by these local moves. Along with those moves, there are some simplification moves, which are sort of analogs of Reidemeister 2 and 1. And this naturally leads to a problem which I think we now know how to solve thanks to Rick Canyon. It's simplification in the sense that there are like two clay, the incidence statements that, okay, like you have two rhombi, for example, that share two consecutive sides. You can remove those two sides and get a single rhombus. No, it's when you look at what is happening, it's that. Yeah, it's not a typo. Yeah, I agree. Life would have been much nicer otherwise. Right? I think there is a phenomenon similar to like uniqueness of Kwasnikov reduction for cladographs that is at play here, that the ultimate reduction will be unique modulo Desargues flips, but anyway, there is some kind of emphasis. It's not about knots, but you can, unify it and then maybe. Okay, so another connection, which I will very briefly outline, is with discrete integrable systems. There is this doctrine by Babianka and Suris that discrete integrability corresponds to 3 or 4-dimensional consistency of discrete dynamical systems. So what it means in this context, it will start with a point and 3 lines, and then select 3 points here, which make the 3 bottom quadrilaterals coherent. Then Desargues' theorem tells us that there exists a unique line that we can place here, which will make the 3 upper parallelograms coherent. Okay, so this we can call this the Desargues dynamical system. So given a point, 3 lines, and 3 points, we can build a line here in a unique way. So this is the propagation rule in Z cubed. And according to the yoga preached by Babianka and Suris, the question that one should ask in situations like this is, does the sequence, does the system exhibit 4-dimensional consistency? So what that means is, and it's a theorem that indeed it does, is that if you play this game on a 4-dimensional cube, so you start with a point and 4 lines and 6 points, and then you construct these lines using Desargues, and then you construct 6 different points here from 6 different cubes, 3-dimensional cubes, that would lead to it. All of those 6 points coincide. And this is the picture that demonstrates that you have the 6 dashed lines all intersect at a point. This is an incidence theorem which I don't think anybody could have come up with without the secret knowledge that I shared with you previously. But it is an incidence theorem. It's a beautiful one. Now, what is the meaning of this theorem? The meaning of this theorem is actually has to do with zoological tetrahedral equation. We start with the zonotopal tiling of an octagon. We interpret the black points as the vertices as points on the plane, the white ones as lines on the plane, and we assume that all these tiles are coherent, which are certain incidence condition. Then we apply Desargues flips to this configuration, and after 8 flips, we come back to the same combinatorics, but they could have been monodromy. The actual points and lines could have been replaced by something else, but they won't be. So, and that's because we have this zoological tetrahedral equation, which is in a way cryptomorphic to 4D consistency. So now I told you about a couple of connections with other kind of mathematics. Let me also, in the last 2 slides, let me tell me about the new insights that this approach provides into the classical subject of linear projective geometry. This setup helps explain conceptually why Pappus theorem is more powerful than Desargues. We can actually deduce Desargues from Pappus using this technology. It's a famous proof due to Hettenberg, notoriously cryptic. We can explain why Pappus and Desargues together, or we can throw away Desargues if you want, imply all other theorems of planar linear incidence geometry. We can explain why Desargues holds over non-commutative skew fields, whereas Pappus does not. Basically, has to do with the fact that fundamental group of the sphere is trivial, but the higher genus it's not. So, kind of the uncommon diagrams technology that would be the non-commutative version of the proof that I gave you would not work on the torus because of the existence of macroscopic cycles. We can explain how to generalize any theorem that you give me. So by gluing in, inserting extra tiles, ask me later, I can explain. We can explain why some theorems can be formulated as closure porisms, as these point-select-tile theorems, whereas some others cannot. This has to do with Hamiltonicity of certain graphs and many other things. And now, further directions. These techniques can be also used to study Panenberg map, its variations, skewers of Tabachnikov, theorems for surface and lines in the Möbius plane, theorems for conics and algebraic curves of higher degree. This is what we are busy with right now as I speak. Theorems involving tangency conditions, Poncelet's phenomena, theorems for surfaces. Over fields of finite characteristic, I can explain how you can use Frobenius to get that as well. Incidence theorems over non-commutative skew fields I already mentioned. Theorems in elliptic hyperbolic geometry, and I'm sure many other things. And that's it. Thank you.